Welcome to the third podcast episode of Radiology AI. My name is Dania Daye, and I'm the Associate Editor for Social Media for Radiology AI. And today we will discuss the 2019 RSNA Brain CT Hemorrhage Challenge and the associate article that was recently published in Radiology AI. Today we have with us Dr. Adam Flanders, who is Professor of Radiology and Co-Director of Neuroradiology and ENT Radiology, as well as Vice Chair for Imaging Informatics at Thomas Jefferson University. Thank you for joining us, Dr. Flanders. I will turn it over to my co-host, Dr. Paul Yee, to start the discussion. Paul?
All right, Dr. Flanders, thank you again for joining us. We're really excited to have you here. Just as an introduction to our listeners, we know that you wear a lot of different hats. You're Professor of Radiology, Co-Director of Neuroradiology, as well as Vice Chair of Imaging Informatics. So can you tell us how you got involved with informatics and AI research? And anything else that you might think would be interesting about your background?
All right, I'll do what I can. First of all, thank you very much for inviting me. And this is always a fun topic to talk about. Let me think. So I have to think way back to the beginning, which is difficult at my age. But I think imaging informatics or informatics in general, I think many of us were drawn to this, I think, in the early days before it even had a name like informatics, meaning we were drawn into the profession of radiology primarily because we saw this great integration between medical diagnosis and computers and the great potential of a lot of the technology that was coming forth, not only on the acquisition side, but also on the processing side. So a lot of people I know my age were very intrigued by radiology because we saw this as a high growth area, an area that was going to change very rapidly in medicine and maybe might be the center of a medical diagnosis worldwide. So I think, at least I can't say everybody that was involved in radiology, but I know I came into it because I had some background in computer programming as a kid. And I think some of the stuff that happened in radiology kind of sparked the similar interest, meaning I saw the applications of computers in radiology and thought, there might be some really great opportunities, at least for some creative thinking or some really interesting research that you could do where you could apply the use of computers in either in doing radiology research. This was long before AI existed and in general. But I think one of the things that I always thought was intriguing, and I think it was interesting to anybody that was involved in computers in general, was this whole notion of being able to train a machine through a computer program to do human-like things, to do a certain kind of task or whatever else. And like a direct offshoot of this is really kind of AI research, because what's more intriguing than teaching a computer or a computer program to do some very human-like things like recognize a pattern or recognize something on an image, which was for many of us is incredibly compelling and very thought-provoking and really exciting. So I think for those of us that got involved in radiology because all the compute that was involved, the AI stuff is even more exciting than the reason why we got into the profession to begin with.
Yeah, definitely. I think that a lot of us can relate to seeing the potential for radiology and potentially transforming how we use data, how we use that ultimately to help patients. And I think it's interesting that even for radiologists of my and Dania's generation, it's really drawing us to the field. In light of that, in the present, we're in 2020, we just had the 2019 RSNA Brain CT Hemorrhage Challenge. Can you tell us about how that came to be? What's the origin story there?
Well, I mean, you guys are probably familiar that, the RSNA has an informatics committee, the RIC, and it has multiple subcommittees, including a data science and a machine learning subcommittee. And the machine learning subcommittee, in conjunction with a lot of the data science group, been putting on these challenges. This was the third challenge that we had done, basically the third challenge that we had done at the annual meeting. First one was to try and determine the chronologic age from pediatric hand x-rays, which is a very standard task that's been done for many, many years in radiology, but to train an algorithm to do that and to do it with a level of proficiency that was equal or exceeded human capabilities. The second one was a pneumonia challenge that was in 2018, and both of these involved radiographs. And so I think those of us on the committee said, you know what, I think we've tested the waters enough. We've kind of developed a proficiency for assembling these data sets. assembling the challenge, getting the competitors together, developing the data sets so that the competitors could train their algorithms and then finally test them. We said, maybe it's time to step up our game. We should maybe focus on a 3D data set. And it seemed like the natural next step forward was to focus on a CT data set, a full CT data set, instead of a single image per case. We figured that was enough for us to bite off to try and get done or to accomplish in a year. So then the notion is that one of some of the fundamental things that the research community as well as the vendor community has been focusing on with head CTs, and it was generally one of the most common things that people have been focusing on is detection of stroke and detection of hemorrhage. So we said, let's focus on the idea of characterizing and classifying hemorrhages inside the head from any variety of causes. Everyone in the group agreed that sounded like a good idea. The only problem was, as opposed to the last two challenges where we had some ready-made data sets that we could work with, we had no images at all. And we had to basically find contributors who could supply us with the needed images. We could then begin the process of developing a data set that we could use for the challenge. But this really all came to pass relatively quickly. I think we decided on it in early 2019 and then spent a long period of time trying to find organizations that could not only assemble images that we could use, but also to get the permission to do this from the respected organizations so that we could go ahead with this. And all of those things ended up being exciting, challenging. We learned a lot through the process, but ultimately told people before it was a nail biter all the way to the end. We basically were running against every deadline and basically making our mark all the way till the annual meeting, and managed to pull it off because, we ended up having over 25,000 unique CT examinations, millions of individual images that we had to assemble and get ready for basically in well less than a year. All of this had to be done became an idea early in 2019, and we basically had to have all the data ready to go by the end of the summer. So a lot of work was put into this on a volunteer basis. A lot of RSNA staff did tremendous work getting this to happen. We had to put a big volunteer group together in order to make it happen from the American Society of Neuroradiology. So it was really, really kind of cool.
Yeah, an undertaking of this size certainly seems like a tremendous amount of effort, just in terms of number of hours that it takes, all of the different sites to coordinate. And I think that for many of our listeners, and particularly for those who read our journal, most of us have probably done some type of AI research, probably on a local single site scale. In light of this kind of multi-institutional, multiple annotator scope of things, could you give us an overview of how that data set curation and annotation process actually went? Because obviously there's a lot of moving parts. If you could just give a summary of that.
Well, yeah, I think the step-by-step process is kind of outlined in the paper, because some of it, I think we likened it to the whole idea of building a plane while it was in flight. It'd be nice if we could do all the steps in order, but we were basically doing things like assembling and curating data from one of our donation sites at the same time while we were refining the data set from a previously submitted site and getting it annotated at the same time. So a lot of the stuff that we had to do from the outset was, once we had the idea ready, we basically solicited people that we thought could contribute some of the data for this. Unfortunately, our colleagues from Brazil were able to contribute data from their site. Our colleagues from Stanford were able to contribute from their site. And fortunately, I was able to contribute a similar data set of about, I think we all had about an equivalent number of exams, about 8,000 exams from each of our sites. And the interesting thing is that all of us used different techniques to collect this data, not only to collect it from our respective PAC systems. Part of it was being able to just say, I only want the head CTs. I only want certain kinds of head CTs. We don't want contrast enhanced head CTs. We don't want head CTs that are mixed in with other types of studies. And we wanted to get head CTs with some very weak labels, meaning that we kind of searched through the reports to try and find the ones that may or may not have had hemorrhage in them, so that we could have data set was focused on the task at hand. But it turned out that's what made the data sets that we assembled from those three sites ended up being heterogeneous from the standpoint of what type of pathologies were on there, because it was either 5 different types of hemorrhage we were trying to subclassify, or not normal, or not normal but not hemorrhage. So it could have been, there could have been a tumor in there, could have been a stroke in there, could have been anything else, but not necessarily hemorrhage. So we had to assemble those sets. We had to have a way to kind of rifle through these thousands of data sets to make sure we had exactly what we were looking for, because you certainly don't want to train a algorithm or train a model on what you think is a head CT, and it's really a CT of the neck, or partly a CT of the chest, or it's a reformatted image of a head, but it's not an axial CT data set. So we had to have a way to curate all the data to try and assemble it. But then, of course, when you're combining it from multiple different sources, one of the great strengths is you have this heterogeneity, not only geographically, different countries, we also have different vendors, different scanners, different reconstruction kernels on the CT scanner. So the data sets were not very similar at all. In fact, they were very different in some ways. But we also had to have a way to combine the data sets so that we had what we thought would be a good true-to-life training data set, as well as a good validation data set, and ultimately a test data set. And on top of all that, we were trying to recruit expert neuroradiologists that were actually going to do the labeling of each head CT. And each head CT had to be looked at by an expert at least once. And for the test data set, we had to have 3 experts look at the same data sets, and we had to have a consensus for deciding whether they classified them correctly. And if they didn't, all of those had to be adjudicated by someone on our panel. So myself and Luciano Prevedella primarily did the adjudication of all the ones where there were disagreements, so that we could make sure that we had the best possible ground truth in evaluating each one of those data sets. And then on top of it, we were doing all of this, but we didn't actually start recruiting people, meaning recruiting ASNR members, until after the ASNR meeting. Basically, we had an open call for volunteers through the ASNR website, and much to my delight, within about a day, we had over 140 volunteers, people that even wrote in and said, I really want to do this. This is what I'm so interested in this topic. I haven't had a chance to get involved in anything, and this sounds like a great way for me to get involved in contributing to some AI research. And I was just blown away by the amount of volunteerism that came from my colleagues in neuroradiology. So as it turned out, we had so many volunteers, we had to turn people away. We could only really kind of manage about 60 people. So we stuck with about 60 of the initial volunteers. We had to train the volunteers. We had to teach them on how to use an annotation tool that we had been using from prior challenges, so that they would know how to look at the studies, how to tag the studies in a particular way, because we had them tag them not only at the exam level, meaning is it normal or not normal, but also on each image, how many different types of hemorrhage could you see on each one of those images. So we did image-based labeling and exam-based labeling. And then we had to have a method to dole out boluses of these exams to each of the 60 volunteers, then monitor their progress on how they were annotating the cases. But before we even did all that, we had to do a check of whether or not they understood what they were doing after we did the training. We had a verification set that they knew how to do the labeling correctly. If there was some misunderstanding, this was an opportunity to retrain them and then get them to work on the data sets. And the amazing thing is that some of the people were so adept at doing this and were so enthusiastic about it. Many of these people did hundreds and hundreds of cases, well over 500, 600, 700 cases alone. And these were volunteers from all over the world, because the American Society of Neuroradiology, like the RSNA, is also an international organization. So we had people from all corners of the globe that were basically working through this data set at a very rapid pace, realizing that we had a very narrow window to get all 25,000 cases annotated. So it was very exciting, very nerve-wracking, but man, we managed to get through it and get it all done in time so that we had the data set prepared, because we have to give all the people who wanted to participate in the challenge, I don't mean the people that had actually done all the sweat equity to help prepare the data set, but the people that, once we advertised the challenge, people from all over the world wanted to have a chance to download the training data, build the most creative algorithm they could think of, the most creative model, to see if they can make it onto the leaderboard. and certainly to see if they can make it in the top 10 and win some of the prize money and get some accolades and have an opportunity to show up at the RSNA and talk about how they solved the problem.
It's definitely an amazing effort, and I think we saw the fruits of those labors with the challenge and how successful it was. But speaking about that, you mentioned how there were annotators from all over the world, all over the country, from different institutions, some really going at breakneck speed to annotate these images. I'm guessing that the platform used had a lot to do with it. So I was wondering if you could talk about the MDAI platform that was used and what factors contributed to choosing it as a platform for dataset annotation, and maybe more generally, what are features that other researchers trying to amass larger data sets might be interested in considering when choosing a platform?
Well, I think the great thing about the MDAI platform, because there are other platforms out there, obviously, and I think part of the reason why we chose it is because we were familiar with it. We'd used it before. It's incredibly flexible. And full disclosure, one of the people on our committee is one of the principals from the company itself. So we basically had an in. We have somebody who could actually help us configure the application so it worked exactly the way we wanted it to work during the whole challenge period. But that being said, it's a cloud-based platform. It's very lightweight, works great on pretty much any browser at all. And it's very simple to use, but it also has the same kind of tooling that a radiologist is used to, meaning, you can easily scroll through a stack of images, window and level, manipulate the image, but at the same time, there's a set of buttons on one side that allows you to rapidly label an image. And since we were not doing pixel-based labeling, meaning we were not asking people to draw regions of interest, we were just basically saying, pick a label for this particular image. This one has subarachnoid hemorrhage. This one has interventricular hemorrhage. This one has both. There was a rapid way to hit those buttons. And there was a rapid way to even go through an entire stack of images where there was a large abnormality that spanned maybe, 10 slices. You could basically say the abnormality starts here and ends here, and it would automatically do all the iterative labeling in between. A lot of time saving involved in that. So people that got facile with the tool could basically run through the data very quickly. Obviously it's easy to label. It's much easier to label the normal ones, but even labeling the abnormal ones, once you got facile with the tooling, you could go relatively rapidly. In fact, we did a lot of projections based on average amount of time you would need to spend even on a complex case. And it turned out once you got facile with the MDAI, you could probably label even a complex case in less than a minute. So we kind of projected forward to figure out with the number of volunteers, the amount of time we have, the amount of time commitment we would expect people to do on average, how many exams we could potentially get labeled by the time we had to fire the finishing pistol and say, we can annotate no more. The reality is we managed to annotate everything we had. It's not like we left anything behind.
So the annotations seem to have worked out perhaps even better than expected. Were there any unexpected challenges or roadblocks that you encountered during this process that you didn't foresee?
Yeah, we learned, first of all, we learned a lot by this process because I'd say, judging by how well the challenge for this year, the pulmonary embolism challenge, which is even on a grander scale than we did last year for the brain hemorrhage challenge, some of the toughest things were coming up with our own novel ways to manage a large group of people. Here we had this army of volunteers that were very enthusiastic about doing this particular task of labeling these head CTs for us, but there were no ready-made tools for managing all the people, doling out boluses of cases for them to work on, checking their progress, all the things that we talked about. So we had to invent a lot of that stuff as we were going forward, to the point where the challenge for this year, they have over 100 annotators from the Society of Thoracic Radiology who have been annotating their data set, and they've been able to manage that because of all the things that the RSNA staff learned by managing a group of 60 people last year. And it was easier actually this year to manage it because we learned a lot from the process going forward to make sure that we didn't leave any gaps. I think we did learn things, particularly when we went back and looked at some of the annotations. Some of the annotations were of better quality than others. And so we took that to heart so that We're doing a lot better quality control this year than we did last year. But interestingly enough, AI is very forgiving in a lot of these ways. Even with imperfect labels, you can actually build a very robust algorithm with imperfect labels. So it wasn't that we needed to strive for perfection, but in this case, I think going forward, we have ways to kind of keep an eye not only on making sure people are getting their work done, but they're being very consistent in the level of quality of work that they're doing. We also found that even though computer programs are not infallible, when you're doing data extraction from our PAC systems, when we think we're getting a CT of the brain, because it says CT of the brain, it helps a lot to look at the images to make sure that's what you're getting, because in certain cases we were not actually getting an axial CT of the brain. So those were cases that we had to throw out. So there were a certain number of cases we actually had to remove from the data set after they had been QC'd. Fortunately, since we'd always lay eyes on every exam, we had the annotators looking at it and saying this isn't a head CT. They could make a comment on MDAI and we would remove it from the data set altogether. But those are some of the snafus that we had going forward. Some of the things that we were worried about that I think were less of a challenge than we thought was de-identification was not a problem. We audited all of our data sets and found no PHI left behind on any of the data, which was terrific. But we also found there was a side disadvantage to the de-identification. Each of our contributing sites used their own unique way to de-identify the data. And as a result, since we use the DICOM data itself, the de-identified DICOM data, there was a way to actually train the algorithm to tell where the data might have originated from. And that created some internal bias. If it turned out, if somebody knew that one of the sites actually had more abnormal studies than another, that could create an internal bias in training a model. So what we had to end up doing with that is we had to rewrite all of the UID labels on all of the studies so that they were very uniform, so that you could not tell in the final data set where any of the exams originated from. That was something we never actually planned for until we started to look at it and realized if there's a pattern here in the DICOM headers, there's a pattern that can be learned by an algorithm in training that we had to remove that piece of bias. So we were constantly doing things to re-clean our data to minimize any kind of bias going forward so that the final data set that folks were training on, validating and testing on was as clean as possible.
Right, so it sounds like there's a tremendous amount learned, and I anticipate that each challenge is going to get better each year. As we near the end of our time, a question that we pose to all of our guests is, what are you most excited about for the next decade in radiology AI or informatics?
Wow, well, I think like everybody else, I think I'm excited about AI because I'm really excited about having a new set of tools that I'm going to get to use in my daily practice. And I'm also excited by the fact that not all the tools that are necessarily things that I have to buy from a vendor. These are things that I might potentially be able to create in my own shop on my own data that would work most effectively in my own environment, which are things that nobody ever thought of before. Very few practices or even university practices can say, you know what, we built our own MRI machine because we wanted something that would do exactly what the type of research we like to do. Most people have to buy things from vendors themselves. A few people actually had enough resources to actually do something like that, to actually build their own devices, but I wouldn't recommend it. What's interesting to me about AI in general, and what's great about computer programming in general, is the playing field is wide open. You know, anybody with a lot of motivation and interest can learn to do a lot of skills that are necessary in order to build something that might actually be a benefit to someone. And of course, that's part of what's so exciting about AI in general, not just in medicine, is the fact that a bunch of smart kids with an interesting set of data can actually maybe solve a really interesting problem out there without having a whole lot of resources. There's a downside to that, of course, because as some many famous people have said, is that there's nothing to stop somebody from thinking that they've cured cancer who have no knowledge about what cancer really is or whatever else, and really kind of go down a rabbit hole and haven't really discovered anything because they don't understand the limitations of their data, the limitations of the problem that they're asking, and so on. But it's the fact that there's so much opportunity out there for people who are interested in this particular technology. And that's why it's exploding in many different directions. But it's not like it's left to a very wealthy vendor in order to do this. There's a lot of great resources out there that let a lot of people. So it may turn out one of the great things that I might be using in my practice 5 or 10 years from now might be something that either we developed in our own shop or somebody down the street actually developed who just had a really good idea and knew how to bring it forth. But it doesn't necessarily mean that it has to come from one of the large companies worldwide in order to do this. So to me, that's kind of the fun stuff about this, because everybody thought when the PC grew up that there weren't going to be any more Steve Jobs or Steve Wozniaks or Bill Gates around anymore, because that kind of thing will never happen again. But the reality is there's a lot of brilliant people in this field. There's a lot of brilliant people in the data science community with some really great ideas and some really amazing approaches to some very intriguing problems. And to me, that's the part that keeps me excited about staying in the game.
Yeah, it's certainly an exciting time ahead. Well, Dr. Flanders, I just wanted to say thank you again for sharing your experiences, your insights, and your wisdoms, and give it back to Dania.
Thank you, Paul and Dr. Flanders, for a great discussion and for sharing with us your insights about the 2019 RSNA Brain CT Hemorrhage Challenge. It was very interesting hearing about what really happens behind the scenes when putting together a challenge like this. I can say that all of us are certainly looking forward to the next RSNA AI challenge this fall. To our listeners, thank you for tuning in to our third podcast episode. Don't forget to rate, review, and subscribe to our Radiology AI podcast series on any of iTunes, Google Podcasts, or Spotify. Please stay tuned for our next episode.